Hey, welcome. Today we're going to be talking through Faraday's law and how it can be used with an example problem, and we need to talk about what an EMF is so everyone knows what's going on with this kind of stuff. First of all, I want to say here's a picture of Faraday right here, and then we also have Lenz as well. So I did just do a screencast on Lenz's law. I'll put a link up in the upper right about now. That is closely related to what we're talking about here. Here are the equations. You may look at that and be like, what the heck is that? Well, I'm going to talk you through it. So we will come back to these equations in a second. But first of all, we need to talk about what an EMF is. So EMF stands for an electromotive force. And so it's the amount of work that would be required to move a charge around a circuit. So it's kind of like how much energy per unit charge it takes to pump from the lowest energetic state up to the highest energetic state. Again, if we're talking about conventional current, imagining positive charges flowing in this direction over here, it's kind of like water that gets put into a pump to pump the water uphill so that the water can then fall downhill and do useful work. I will say too that EMF is measured in volts, just like potential difference. So it's related to potential difference, but it's not exactly the same thing. So that's an introduction to EMF and what we mean by it. Let's take a look at these variables here so we don't get overwhelmed. I know there's a lot on this page, but let's get to it. First of all, N just represents the number of loops that the electrons can go around. So we're talking about a loop of wire or multiple loops of wire. This delta is delta phi or phi, and that's going to be the change in the magnetic flux that we see up here. Or we could break down what magnetic flux is, and that's going to be the magnetic field times the area through which the magnetic field goes through, times the cosine of theta, where theta has the reference line for the angle being perpendicular to, or a normal to, the magnetic field line that comes through. So effectively we're saying how much does the magnetic flux, how much magnetic field is in a certain area, let's say a loop of wire for instance, how much does that change per unit time, and then based on that we get an EMF. And so this is where I talked about this previously with the Lenz law screencast, but the idea is that there's going to be a current in this loop that resists the change of the magnetic field that's coming through. And what we're doing is quantifying that. We're figuring out with Faraday's law, all right, how much is that EMF that's generated, that's induced from the changing magnetic flux? And that's what we're looking at here. So let's see if we can start to put this into a problem. So let's say this is another way of visualizing what we're talking about with measuring that angle. I'm adding that in because I think measuring that angle and really understanding what's happening with the angle is important and a little bit difficult to do. So notice this is a normal line to the plane of the loop. So if we have a loop up and down like this, and then a deviation from that would be your cosine of the angle that you measure. Alright, so we have two different versions of the equations up here. Let's say a problem gives us there are going to be 17 turns or loops. We know our area over here. We know what the external magnetic field initial is. That's going to be 0, and it's going to change to a value of 0.55 Teslas over 0.85 seconds. So there's a change in the magnetic field, like a rotating loop or something. And the question is how much current is going to be induced in this coil of wire. So if you take a look down here, this is our coil of wire, and the magnetic flux is increasing. It's going to go from right to left. It's going to go in that direction, and that's going to cause electrons to flow around in this loop. And that's what we're talking about right here. Notice that there is a resistor in this little mini circuit, but there's no power source. You can actually get electricity from moving magnets, or changing magnetic fields, you could say. And that's fundamentally what we're talking about, and that's the basis for electrical generation. Alright, so let's see how we go about doing the problem. Let's think about this. So first of all, we can plug in, we know we have 17 loops. Now this loops here is more of a descriptor. It's not so much of a algebraic unit that needs to be canceled out. It's more like a label, kind of like degrees or radians. So, and then we start to think about what's happening here. Remember, the initial magnetic field was 0, so we can actually drop this term out, and that's what we'll do on the next slide. So taking a look up here, this is what we had worked with the previous line, so to speak. I can drop that out. We can start to plug in some numbers and think about what's going to happen here. So there is an induced EMF, electromotive force, which causes those electrons to move, you could say, and that's going to be a negative 19 volts for this system right here. All right, well, the question though isn't for this, although this is a good answer to get to. This could be an answer to a question. The problem could have asked about this, like what's the induced EMF when you have this scenario. But if we take it one step further and say find the magnitude of the induced current in the coil, then what we could do is, what do you think? Something that you may not have thought about for a while. Can you see where we're going with this? Think about it. Currents, we've got a resistance, we've got an EMF going on. Any idea what equation we could possibly use for this? Well, what we could use would be Ohm's law right over here. So this EMF is similar to a potential drop or a potential difference, and we're looking for I. We're looking for current. So let's go ahead and isolate for current, and then we can plug in our numbers and we can solve, and we get the idea that it's going to have an induced current of 5.8 amps for this scenario. If you have an increasing magnetic field or an increasing flux scenario, it causes a current in that coil of wire, and that's the foundation. If you've understood what I've said, more or less, that's the foundation of our modern society, because based on that we can have electrical generation. If you have a moving magnet or a moving magnetic field, that causes current in a nearby conductor, that kind of thing, and the reverse is true as well. So generation as well as motors are now possible if we understand this as a society. I'm going to get to eventually explaining how motors and generators work, so stick around for that. And if you have any comments down below, please let me know, and I hope you all have a great day. Take care.